In that quiet region around a massive star, nothing seems to hurry, yet the star is steadily reshaping space with invisible winds. Layers of gas drift outward, faint arcs appear, soft shadows form where dust gathers. This is the slow architecture of a supergiant's final years. If you enjoy calm science-rich sleep documentaries like this one, please tap like to support the channel and subscribe for more long-form journeys through deep space with new stories designed for restful listening. Now let the winds unfold. A supergiant can look steady, yet its surface is already unfastening into space. Over its late life, it can lose about the mass of the sun. It is like an entire ocean of gas turning into a drifting fog with no shoreline. Along the bright edge, a thin veil hangs in place. It trembles, then slides outward in slow motion. The first unlock is simple. A star does not need an explosion to reshape its surroundings. A wind alone can sculpt a future nebula. In that region, light behaves as a steady pressure. Gravity still pulls inward, yet the outward push never fully stops. The scene begins at the limb where glow fades into dark. A soft gradient forms from bright to faint. The boundary is not sharp. It is a layered atmosphere that thins by degrees. A second unlock settles in. The wind is not a uniform stream. It is a textured outflow with knots and gaps. Those textures later appear as arcs and shells in nebulae. The atmosphere shows faint ripples like wind lines on a calm lake at night. The ripples do not race, they drift as if time itself is thicker there. The core mechanism fits inside one calm idea. Radiation pressure transfers momentum from light to gas. A definition arrives and stays brief. Radiation pressure is the gentle push carried by flowing light. It works like warm air lifting mist off a heated surface. It also works like sunlight nudging pollen through still air. It matters because a supergiant shines so strongly that the push adds up. The wind begins where the push can keep gas from settling back. At this distance, the surface looks like a sphere of fire. Up close, the edge becomes a banded glow. Thin layers stack like translucent fabric. Each layer has its own density. Each layer has its own speed. A small payoff appears as a question resolves. Why does the wind accelerate after it starts? The answer sits in the thinning air. As gas rises, it becomes more transparent. Light reaches deeper into it. The push acts on more particles at once. The outflow strengthens as it climbs. The wind does not need a single launch. It builds itself step by step. A new visual anchor slows the pacing. A faint halo surrounds the star like breath around a cold stone. The halo is brighter in some directions. It dims in others. Soft scallops form along the edge. Those scallops mark places where gas is denser. The second concept arrives without crowding the first. Line driving shapes the wind by selective absorption. A definition stays short. Line driving is light pushing through specific absorbed colours. The absorbed colours act like tiny handles in the gas, like a sail that catches certain gusts more than others, like leaves that flutter when a narrow draft finds them. It matters because it can amplify the push in the upper layers. The wind can then reach higher speeds. It can also become unstable. A quiet unlock lands. Instability is the seed of structure. The wind breaks into clumps because the push is uneven. Some parcels catch more light. They surge ahead. Some catch less. They lag behind, faster. Gas collides with slower gas. Compression forms thin ridges. Those ridges can cool and thicken. They become the first scaffolding of a future nebula. The scene shifts from smooth veil to flecked spray. Brightness comes in grains. Darkness comes in gaps. The atmosphere resembles a dandelion puff shedding seeds into still air. The seeds are not identical. Some drift as single specks. Some drift in small clusters. The analogy stays gentle and clear. The scale shift begins to widen. A clump can be as large as a planetary orbit. It can also contain filaments far thinner than that orbit. The same wind holds both extremes. Seconds pass at the surface. Thousands of years pass in the expanding shell. The outflow carries the star's history outward. Each layer becomes a timestamp in gas. A small payoff answers another question. Why do nebulae show arcs instead of perfect spheres? The answer begins here. The wind is already anisotropic in practice. Clumps favour some directions for a time. Shocks carve thin curved surfaces. The star's rotation and surface patterns can bias the flow. The result is not a flawless bubble. The result is a weather system written in plasma. The visual anchor returns as a new scene. A set of faint curved bands drifts away. Each band is brighter along its crest. Each crest marks a compressed front. Between crests the gas is more rarefied. The pattern is like ripples frozen into a fog bank. A limit of intuition arrives and stays soft. The flow cannot be watched directly in detail. The outer layers are too bright and too far. Many structures are inferred from light alone. Line shapes change and suggest density changes. Brightness changes and suggests temperature changes. Different explanations can mimic the same signal. The limit is one of resolution and degeneracy. Small clumps can hide inside broader layers. Thin shocks can blur into smooth gradients. A model can fit, yet another model can also fit. The wind remains partially indirect knowledge. That limit does not weaken the story. It clarifies what the wind truly is. It is a process glimpsed through its effects. The effects remain physical and concrete. A gradient in brightness marks a gradient in density. A sharper edge marks a shock front. A faint ring hints at a swept shell. Those shapes are the wind made visible. A gentle checkpoint follows. The wind removes mass. Mass changes the star's future. When outer layers leave gravity at the surface changes. The star's radius can adjust. The internal balance shifts. The same wind that shapes nebulae also steers the final collapse path. A small payoff locks this connection. Mass loss is not decoration around a star. It is the script that sets the stage. The environment becomes a medium shaped in advance. A later blast wave will not meet empty space. It will meet cavities and ridges. It will meet dust and dense knots. It will brighten where gas is thick. It will fade where gas is thin. The wind decides those contrasts early. The scene slows again to keep the rhythm even. A wide shell expands into darkness. Its inner face is slightly brighter. Its outer face is softer. The shell is not smooth. It carries dim lumps like beads in a translucent curtain. The shell drifts outward in sipency. The star remains at the centre as a steady lamp. The lamp does not chase its own wind. The wind simply continues. Another scale shift arrives with care. Near the surface, a parcel crosses the first layer in minutes. Farther out, that same parcel takes years to double its distance. Later, it takes centuries to reach the next shell. The pace slows in feeling as distances grow. Space is wide. Time stretches with it. The wind becomes a calm conveyor. It carries material from dense heat into thin cold. It carries momentum from light into motion. It carries structure from instability into geometry. The closing transition stays gentle. The next step moves closer to the threshold where gas escapes at all. It turns from the broad halo to the subtle balance at the surface. It follows gravity and the first lift into the wind. At this distance, the star's edge looks like a calm shoreline of light. The wind begins where outward pushes match gravity in the thinnest layers. The first image holds steady. A pale limb shows a smooth brightness gradient. It fades from a hot core glow to a faint rim. The rim is not a hard line. It is a stack of layers that thin outward. A small unlock arrives early. The wind does not start as a jump. It starts as a slow leak across a soft boundary. The key balance is set by two ideas: effective gravity and escape. Effective gravity is gravity reduced by outward forces. Escape is the point where rising gas does not return. A gentle analogy carries the balance. It resembles dew on a leaf at dawn. The droplet holds until the surface tilt changes. Then it slides without a dramatic break. It matters because the same quiet threshold decides where mass loss begins. The scene tightens closer to the atmosphere. Thin sheets of gas drift above the luminous surface. They move as if they hesitate. Some parcels lift and fall back. Others cross a point of no return. The wind begins with those few. A small payoff resolves a question. Why can such a massive star lose gas at all? The answer is not weak gravity. It is the combination of huge radius and relentless outward pressure. A supergiant spreads its mass over an enormous surface. Its pull at the edge becomes comparatively gentle. Light adds a steady outward nudge. The two together reshape the boundary. The next visual anchor appears. A faint ring of haze forms just above the limb. It is brighter along one arc. It is dimmer along another. The ring suggests uneven density. It also suggests motion across layers. The second concept enters without crowding. Scale height sets how quickly density falls with height. Scale height is the height where density drops by a large factor. A warm atmosphere has a larger scale height. A cool one has a smaller scale height. It matters because it sets how thick the launching region is. A small unlock settles in. A thicker launching region gives the wind more room to organize. It also gives instabilities time to grow. The atmosphere becomes a place of gentle sorting. Denser gas lingers lower. Thinner gas rises farther. Light finds paths through the thin parts first. The push becomes patchy. Patchiness becomes structure. The analogy shifts to something everyday and new. It is like foam on slowly moving water. Some bubbles merge and thicken, others pop and vanish. The surface remains calm while the texture changes. The wind begins with texture, not with uniform flow. The scale shift widens across time. A parcel can hover near the threshold for minutes. A shell produced by many parcels can drift outward for thousands of years. The same process spans both. A small payoff answers another question. Why do later nebulae show shells? The answer begins with layering near launch. Each period of slightly stronger outflow thickens a layer. Each calmer period leaves a thinner gap. Over time, those differences move outward. They stretch into arcs. They remain as faint edges. The next visual anchor holds the eye. A set of thin nested curtains expands away from the limb. Each curtain is slightly brighter at its leading edge. The edge is a compressed front. Behind it, the glow softens. The curtains do not race. They drift as if suspended in clear water. A limit of observation arrives and stays precise. The launching region is small compared to the distance. It is also drowned in glare. Fine structures near the limb blur into a single band, and many details are inferred from how light scatters. Brightness can change from density or temperature. Different causes can look similar. This is a limit of resolution and inference. The boundary can be described. It cannot always be mapped in detail. That limitation shapes how models are built. Models often simplify the launch into smooth layers. Real winds often begin clumpy. A small payoff follows from that limit. Even a simplified launch can predict the broad flow. The broad flow sets where shells appear. It sets how quickly the wind thins. It sets how a later shock will propagate. The fine details matter for texture. The broad balance matters for shape. The physical detail stays concrete. The limb shows a narrow, bright band. Above it, a softer halo rises. Within the halo, faint streaks tilt outward. The streaks mark shearing flow. Shear means neighbouring layers move at different speeds. The shearing stretches clumps into filaments. Filaments become the strands seen later in nebulae. The analogy remains calm and singular. It is like taffy pulled slowly. A lump becomes a ribbon. A ribbon becomes a thread. The pull is gentle. The change is steady. The scale shift widens again. A thread may be thinner than a planet's orbit. The structure it adjoins can span distances far larger than that orbit. Small differences at launch become large geometry far away. Another visual anchor arrives to keep rhythm. A faint arc appears where a denser layer catches more light. The arc curves around the star. Its curve is not perfect, it has subtle breaks. Those breaks hint at clumps inside the layer. The wind carries those breaks outward. They become the seeds of knots. The closing transition stays soft. The next step moves from the launch threshold to the pushing force itself. It follows how light transfers momentum through selected colours. It lets the wind accelerate and fragment in a calm way. Light can feel weightless, yet in a supergiant's upper air it behaves like a steady hand. The wind accelerates because certain colours of light grip the gas more strongly. In that region, light behaves as a pressure field that is uneven by nature. The scene begins as a bright rim with a thin, translucent veil. The veil is not smooth. It shows faint streaks that tilt outward. Each streak marks a channel where gas thins. Each channel lets light penetrate farther. A small unlock settles early. The wind gains speed by becoming patchy. Patchiness is not a flaw. It is the way the push concentrates. The first concept stays simple. Opacity controls how much light interacts with gas. Opacity is how strongly material blocks or absorbs light. A foggy window has high opacity. Clear glass has low opacity. It matters because the push from light grows where opacity rises in the right places. The story turns to the second concept without crowding it. Line driving gives light those right places to grab. Line driving is acceleration from light absorbed in narrow colour lines. Those lines act like tiny doors that open for a moment, like wind catching a row of hanging ribbons. Some ribbons catch more gusts than others. It matters because those selective pushes can beat gravity in the outer layers. The wind begins slow and then steepens. The main number arrives and stays rounded. The wind can reach about 2,000 kilometers per second. That is like crossing a continent in minutes. The number is not the point by itself. The point is the gradient that produces it. Close to the star, the flow is dense. Farther out, it thins and speeds up. A visible detail follows the gradient. The halo shows a brighter inner band. It fades into a darker outer region. The change is not gradual everywhere. Thin edges appear like knife marks in mist. Those edges are shock fronts where fast gas overtakes slow gas. A small payoff answers a question. Why do later nebulae look clumpy? The answer begins here. Line driving is unstable. A slightly denser patch absorbs more light. It is pushed harder. It becomes faster. It then catches up to slower material ahead. Compression forms a clump. The clump becomes a bright knot in scattered light. The scene shifts to a single visual anchor that stays unique. A long curved streamer peels away from the limb. It looks like a pale ribbon unrolling in the dark. The ribbon is brighter at its spine. Its edges are softer. Behind it, a faint wake spreads like smoke in still water. The streamer is not a straight line. It bends with the flow. It shows tiny scallops along one side. Those scallops mark shear where layers slide past each other. Another small unlock arrives as a quiet correction. The wind is not a constant blast, it is a layered traffic of parcels. Faster parcels create shocks. Slower parcels fill the gaps. The overall outflow remains steady on large scales. On small scales, it is restless. The scale shift widens gently. A shock can form over minutes near the star. Its imprint can travel for thousands of years as it expands outward. The same shock becomes a faint arc far away. The arc becomes a boundary in a later nebula. The analogy changes and remains singular. It is like a fountain made of fine mist. The overall plume rises smoothly. Inside it, tiny jets and swirls appear and vanish. The plume is one shape. The interior is many brief patterns. This matters because the wind's texture becomes the nebula's texture. The next visual anchor keeps rhythm without repeating the main one. A thin shell appears as a dim crescent in the halo. It is brighter along its leading edge. Behind it, the glow fades. The crescent is a compressed layer. It is built from many collisions of parcels. A small payoff resolves another question. Why do arcs look like rings? The answer is geometry. A curved shell seen from afar can project as a ring. The shell does not need to be a perfect sphere. It only needs a thin, bright edge. The eye reads edges more strongly than interiors. The wind naturally creates edges through shocks. A limit of observation enters and stays specific. The narrow colour lines that drive the wind overlap and blend. Many lines sit so close that they behave like a forest. It becomes hard to identify which lines dominate. It is also hard to measure clump sizes directly. Brightness variations can come from density or from temperature. Spectral signatures can be smeared by motion. This is a limit of disentangling causes, not a lack of signal. Models approximate the line forest. They also approximate clumping with simple factors. Those approximations can capture bulk acceleration. They can miss fine structure. The limit matters because predicted mass loss can shift with assumed clumping. A small payoff follows from that limit. Even if clump details are uncertain, the wind's tendency to fragment is robust. Any selective push can amplify small inhomogeneities. Fragmentation then sculpts the circumstellar medium. The physical detail returns to keep the scene grounded. The halo shows faint graininess. Thin filaments radiate outward. Some filaments merge into broader lanes. Some dissolve into diffuse haze. Where filaments cross, brightness increases slightly. That indicates denser knots. Knots cast subtle shadows in scattered light. The shadows are not sharp. They are soft gradients that trail behind. The scale shift widens once more and stays calm. Near the star, a filament's width can be smaller than a planetary orbit. Far away, the same filament can span distances larger than that orbit. Expansion stretches it. Cooling changes its brightness. Time makes it into a memory. The closing transition stays gentle and forward. The next step moves from light pushing gas to gas, creating new material. It follows how cooler winds allow dust to form and ride outward. It keeps the motion slow and the shapes clear. A cooler supergiant turns its own wind into a dim workshop where solid grains can appear. Dust forms because the outflow cools and becomes dense enough for atoms to stick. At this distance, the halo shifts from bright glare to a softer reddish haze. The light looks filtered. The edge of the glow becomes smoother in some places. In other places, it shows darker lanes where material thickens. A small unlock arrives early. Dust does not only ride the wind, dust helps the wind by giving light a better grip. The first concept stays gentle. Condensation turns gas into solid grains in cooler layers. Condensation is gas sticking into solids when it cools enough. It resembles breath turning into frost on a cold surface. It also resembles steam forming tiny droplets in morning air. It matters because grains interact with light efficiently. A second concept joins without crowding. Scattering redirects light when it meets small particles. Scattering is light changing direction after hitting small particles. It looks like a headlight beam in fog. It also looks like sunlight in a misty valley. It matters because scattered light can push on grains. The wind gains another handle. The main number arrives and stays simple. Dust begins to survive at about 1000 degrees. That is like a kiln cooling from glowing orange to dull red. The number is not a precise boundary. It is a rough threshold where grains last longer than they evaporate. In that region, the wind becomes layered by temperature. Close in, the gas is too hot. Farther out, it cools and thickens. The physical detail becomes clear. A thin shell shows a sharp inner edge. Outside it, a broader band fades gradually. The inner edge marks where conditions flip. The outer fade shows where dust density drops. A small payoff answers a quiet question. Why does the nebula later appear dim and red? The answer begins with dust. Grains absorb and scatter shorter light more strongly. The remaining glow shifts toward redder tones. The same grains also emit gentle heat as infrared glow. That emission becomes a soft background. The wind turns from a bright veil into a warm, muted cocoon. The unique visual anchor settles in and remains central. A broad, faint disk of dusty haze surrounds the star. It is not a solid disk. It is a flattened glow with a darker lane across its middle. The lane is a shadow cast by denser dust. The shadow is soft and wide. It stretches outward like a charcoal smudge. The scene stays slow. The dust lane does not flicker. It drifts outward with the wind. A small unlock follows the image. Shadow reveals structure without needing sharp edges. Even when detail is blurred, a shadow lane indicates geometry. It suggests a denser equatorial outflow or a thicker band of dust. The wind is no longer only plasma texture. It becomes a sculpted light filter. The analogy remains unique and calm. It is like a lantern placed behind thin fabric. A single fold makes a darker stripe, a thicker fold makes a broader shadow. The lantern itself stays constant. The pattern comes from the fabric. Dust plays the fabric in the stellar wind. The scale shift widens gently. A grain is smaller than a speck of smoke, yet many grains together can dim a shell as wide as a solar system. Over thousands of years, that shell expands to distances where it becomes a nebula boundary. The same grain also changes the chemistry of the outflow. Elements lock into solids. Later shocks can shatter grains and release atoms again. Another visual anchor appears to keep rhythm without repeating the main one. A faint arc brightens at one side of the dusty disk. The arc looks like a crescent. Its crest is slightly sharper. Behind it, the glow softens into haze. This crescent is a compressed dust ridge. It forms where wind parcels collide. Dust collects where gas compresses. A small payoff resolves a question. Why do some nebulae show rings and arcs? The answer is dust enhancement in thin ridges. A ridge has more particles per volume. It scatters more light. It also blocks more light behind it. The ridge becomes visible as an edge. The interior remains faint. The eye reads the edge as a ring. The story touches a limit of observation with care. Dust both reveals and hides. It can block the inner regions from view. It can also mimic density changes through changing grain sizes. The observed color depends on composition and size. Two different dust mixtures can look similar in broad light. This is a limit of inference from color alone. It is also a limit of spatial resolution. A shadow lane can be broader than the structure that makes it. Models must assume grain properties. Those assumptions affect derived mass loss. A small payoff follows from that limitation. Even if grain details vary, the role of dust as a light coupler remains. Where dust is present, radiation pressure on grains can accelerate the flow. Grains drag gas by collisions. The wind can become stronger without needing hotter gas. This connects back to the larger arc. Mass loss can increase as the star cools. The wind changes character with temperature. The physical detail returns to keep the scene grounded. The halo shows mottled brightness. Dark pockets appear as soft-edged holes. Those holes are not empty. They are regions where dust blocks forward scattering. Around each pocket, a thin, bright rim forms. The rim is a limb effect where the line of sight crosses more dust. The motion remains slow. The pockets widen as the shell expands. The scale shift widens again. Near the stardust forms over hours as gas cools. Farther out, the same dust lane persists for thousands of years. Over that time, it becomes a record. It marks episodes of stronger or weaker outflow. It marks where shocks passed. It marks where geometry stayed consistent. The closing transition remains gentle. The next step moves from dust and light to the wind's internal collisions. It follows how shocks and compression create layered shells. It keeps the pace soft and the shapes clear. A wind can sound like a single flow, yet it often becomes a sequence of quiet collisions. The layered look of many nebulae begins as faster gas runs into slower gas and builds shells. At this distance, the outflow resembles a faint mist, yet thin edges appear like drawn arcs. Those edges are real boundaries. They are places where density jumps across a narrow front. The first unlock arrives early. Shells form without any eruption. A steady wind can create them through speed differences alone. The first concept stays simple. A shock is a thin region where flow conditions change abruptly. A shock is a narrow front where gas compresses and heats. It resembles a wave breaking into a thin white line. It also resembles a fast breeze meeting a slower fog bank. It matters because shocks gather material into visible layers. The second concept joins without crowding. Compression increases density and strengthens cooling. Compression is squeezing gas into a smaller volume. It is like packing fluffy cotton into a tighter wad. It is also like snow pressed into a firm layer. It matters because compressed gas can radiate energy and become thinner in temperature. That cooling helps a shell stay narrow. The visual anchor settles and remains unique. A translucent bubble wall expands around the star. The wall is not uniform. It shows a corrugated edge like gentle scallops. Each scallop is a ripple where parcels have piled up. Inside the bubble, the glow is softer. Outside it, the haze fades into dark. The wall looks like a soap film seen in low light. It is thicker along a bright rim. It is thinner between rims. A small payoff answers a question. Why do shells stay thin instead of smearing out? The answer is cooling after compression. When gas compresses, it heats briefly. Then it radiates energy and cools. Cooler gas occupies less volume at the same pressure. The shell narrows into a sharper boundary. The next visual anchor appears to keep rhythm. A second faint wall forms behind the first. It is weaker. It is also closer to the star. Two walls drift outward in parallel. The spacing between them slowly grows. This spacing is a record of wind history. The main number arrives and stays rounded. A shell can remain recognizable for about 10,000 years. That is like a mountain range persisting while weather slowly rounds its peaks. The number serves scale rather than precision. The shell begins near the star and travels outward. Over that time, it moves from a region the size of a planetary system to a nebula-sized structure. The scale shift widens with calm pacing. Near the star, a faster parcel catches up within hours. Farther out, the same chase can take years. The change happens because distances grow. The shell becomes a long-lived pattern. The wind becomes a slow archive. Another small payoff settles in. The shell spacing can imply when wind speed changed. A brief increase in speed sends a faster layer outward. It catches slower gas and forms a new shock. A calmer phase leaves a gap. Many gaps become many shells. The nebula later looks layered because the wind is variable in detail. The variability does not need drama. It can come from gentle changes in surface conditions. It can come from clumping in line driving. It can come from dust coupling. The physical detail stays concrete. Along the shell edge, brightness peaks in a narrow ridge. Behind the ridge, the glow drops quickly. This is a density gradient. It is not a smooth fade. It is a sharp step that indicates compression. Small knots sit on the ridge like beads. Each knot is a denser clump caught in the shock. A soft shadow trails behind some knots. The shadow is a region where less light scatters forward. The analogy remains unique and calm. It is like a slow river meeting a line of reeds. Water piles up at the reeds. A narrow band of foam appears. Leaves collect in that band. The band moves downstream as a coherent line. The foam band is the shell. The leaves are the knots. The river remains the wind. A new visual anchor arrives to keep the cadence steady. A thin crescent brightens where the shell curves toward the line of sight. The crescent is brighter than the rest of the wall. The brightness comes from a longer path through the compressed layer. The rest of the shell remains faint. This explains why arcs can dominate an image. Edges carry more contrast than interiors. A small payoff follows at once. The shell can look like a ring even if it is only a partial bubble. Projection emphasizes rims. A curved surface seen at a tangent becomes brighter. A surface seen face-on becomes dim. The eye reads the rim as structure. The shell exists everywhere. Visibility concentrates at the edge. A limit of observation arrives and stays precise. Shell thickness is hard to measure directly. The shell is far. Its boundary is blurred by line of sight mixing. Different layers overlap in projection. A thin shell can appear thick if tilted. A thick shell can appear thin if the brightness is concentrated at a rim. This is a limit of geometry and resolution. It is also a limit of inferring density from light. Emission depends on temperature and ionization. Scattering depends on dust content. A single image cannot separate these cleanly. Models use assumptions about cooling and composition. Those assumptions change inferred mass loss. A small payoff follows from that limitation. Even with uncertain thickness, the presence of sharp rims indicates shocks. Shocks imply speed differences. Speed differences imply a wind that changes over time. The layered nebula is therefore a signature of wind variability. It is a physical message that survives long after the surface patterns change. The scene returns to the expanding bubble wall. Its corrugated edge relaxes as it grows. The scallops widen. The knots drift apart. The wall remains a boundary. It carries momentum outward. It also defines a cavity inside. That cavity is lower density. It will later shape any stronger event. The scale shift widens once more. A small clump formed near the star becomes a knot larger than an orbit. A shell made from many knots becomes a structure larger than a star system. Time stretches as the shell drifts. The ending transition stays gentle. The next step moves from shells formed by collisions to the deeper cause of variability. It turns toward large surface motions that pulse and churn. It keeps the wind quiet and the geometry slow. A supergiant surface appears smooth from far away, yet it is stirred by slow, gigantic overturning. Convection seeds the wind by wrinkling the atmosphere and feeding uneven density into the outflow. At this distance, the visible disk shows soft mottling. Bright patches drift and fade. Darker patches gather into broad lanes. The limb reveals a subtle scalloped edge where hot and cool regions meet. The first unlock arrives early. The wind inherits its first texture from below the surface. It does not need shocks to begin clumpy. The first concept stays calm. Convection is heat carried by rising and sinking material. Convection is bulk motion that transports heat through moving fluid. It resembles thick porridge rolling in a pot. It also resembles slow clouds rising and settling in a calm sky. It matters because it reshapes density at the base of the wind. Those density variations become launch points. The unique visual anchor settles and remains central. A single giant cell dominates the surface. Its center is brighter and slightly hotter. Its rim is darker and cooler. Along the rim, a curved boundary forms like a broad ring. The ring is not complete. It breaks into segments. Each segment is a place where gas piles up before lifting away. The scene is slow and steady. Nothing flashes. The edges drift. The second concept arrives without crowding. Turbulence is irregular motion that breaks flow into many scales. Turbulence is chaotic mixing across many sizes of eddies. It is like cream stirred into coffee until swirls turn into fine threads. It is also like smoke that folds into curls, then into haze. It matters because it turns a smooth wind into a patterned wind. Even before radiation pushes hard, turbulence creates clumps. A small payoff answers a quiet question. Why do some clumps look rooted near the surface? The answer is that the surface is not uniform. Rising plumes carry lower density gas upward. Sinking lanes concentrate denser gas. When light pushes outward, it finds paths through thin regions first. Those paths become channels. Channels then feed faster outflow. Denser lanes resist and lag. The wind begins with an imprint of the convective map. The main number arrives and stays rounded. A convective cell can span about the width of the sun. That is like a single wave as wide as a planet's whole sky. The number carries scale without precision. It also frames the next shift. The cell evolves over days or weeks. The wind it seeds can persist for thousands of years as it expands. A small unlock settles in. A short-lived surface pattern can become a long-lived nebular arc. The pattern is stretched outward like paint pulled into a long stroke. The next visual anchor appears to keep rhythm while staying secondary. Above the bright cell, a plume of gas rises. It forms a translucent dome. The dome is brightest at its edge. The center is dimmer. The edge indicates a thicker path through gas. The dome slowly leans as the flow shears. Its top becomes a faint streamer. The streamer drifts outward and thins. A small payoff resolves another question. Why do nebulae show curved filaments instead of straight rays? The answer is shear and rotation in the outflow. Layers at different heights move at different speeds. A rising plume is stretched sideways as it ascends, its boundary curls, that curl becomes a filament. The filament remains curved because it forms on a curved surface. The star's atmosphere is a sphere. Curvature is inherited. The physical detail remains clear. The plume edge shows a sharp brightness gradient. Just inside the edge the glow is stronger. Just outside it the glow drops quickly. This indicates a density step. The step is not a shock. It is a boundary between a plume and its surroundings. Such boundaries persist long enough to guide later acceleration. They are like grooves in the flow. The analogy remains unique and calm. It is like bread dough rising under a thin skin. Bubbles push upward. The skin stretches and forms seams. Some seams become ridges. When the dough expands, ridges lengthen into lines. The dough is the atmosphere. The ridges are density lanes. The wind carries those ridges away. The scale shift widens again. A seam that forms over minutes near the surface can stretch into a filament that spans an orbit. Over centuries it becomes part of a shell edge. Over millennia it fades into the larger nebula glow. The same feature changes roll with distance. Near the star it is a launch guide. Far away it is a faint thread of structure. A limit of observation arrives and stays precise. The surface patterns are hard to map cleanly. Brightness changes can mean temperature changes. They can also mean opacity changes. Many features overlap along the line of sight. Fine cells can blur into broad mottling. This is a limit of resolution and interpretation. Models often represent convection with simplified cells. Real convection includes many interacting scales. This affects predicted clump sizes. It also affects predicted mass loss variability. A small payoff follows from that limitation. Even without perfect maps, the need for large-scale overturning remains. A supergiant must transport heat. Convection is the natural route when radiation alone is not enough. That transport inevitably makes patterns. Patterns inevitably seed wind texture. The scene returns to the giant cell ring on the surface. The ring segments drift like slow continents. At their edges, gas rises. Above them, the base of the wind looks grainy. The graininess is not random noise. It is the atmosphere reorganizing itself. The wind begins to pick favorites. Some paths become clearer. Some become clogged. The future nebula begins as a changing map of soft boundaries. The closing transition stays gentle. The next step moves from steady overturning to slow pulsations. It follows how rhythmic expansion and contraction can loosen more material. It keeps the motion even and the edges calm. A supergiant can breathe without sound, expanding and settling in slow cycles. Pulsations loosen the outer layers by repeatedly lifting them into thinner air. At this distance, the star's rim appears to swell and relax. The brightness at the limb shifts in a gentle rhythm. A faint ring of haze thickens, then thins. The first unlock arrives early. A wind becomes easier when the surface is periodically raised. The push from light has less work to do. The first concept stays calm. Pulsation is a global oscillation of a star's outer layers. Pulsation is a repeated expansion and contraction of stellar layers. It resembles a deep swell on a quiet sea. It also resembles a slow bellows opening and closing. It matters because it changes density at the wind's base. When the star expands, the outer gas cools and becomes less tightly bound. When it contracts, some gas falls back. Some gas stays aloft. That leftover becomes the seed of mass loss. The unique visual anchor settles and remains central. A thin, luminous shell hovers above the surface like a detached skin. The shell is brightest along its edge. Its center is faint and diffuse. The edge looks sharper when the star is expanded. It looks softer when the star settles. The shell drifts outward a little, then pauses. It does not return fully. It becomes a layered boundary that slowly migrates away. A small payoff answers a quiet question. Why does a repeating motion produce a one-way loss? The answer is that the cycle changes the escape threshold. During expansion, effective gravity weakens at the rim. Gas lifted a small distance can cross a point where it no longer returns. During contraction, the base sinks inward. but the lifted parcel is already farther out. Light and pressure gradients can then keep it from falling back. Over many cycles, small leftovers accumulate into a steady outflow. The second concept arrives without crowding. A compression wave travels through the atmosphere during pulsation. A compression wave is a moving region of higher density and pressure. It resembles a slow ripple passing through fog. It also resembles a wrinkle moving across a soft cloth. It matters because it can steepen into a shock in the upper layers. That shock can make a thin ridge. A ridge is a place where dust or gas gathers later. The physical detail stays concrete. The detached shell shows a narrow bright rim. Just behind the rim, a darker lane appears. The lane is a shadowed region where density is higher. The rim marks a compressed front. The lane marks material that lags behind. The boundary is not perfectly round. It has gentle bumps that drift sideways. Those bumps come from convection and turbulence below. Pulsation amplifies them by lifting the whole map. The main number arrives and stays rounded. A pulsation cycle can last about 1 year. That is like seasons passing, yet the star does not change its place. The number frames the scale shift. The lifted gas changes over months. The shell it forms can persist for thousands of years as it drifts outward. The same rhythm that is slow on the surface becomes almost frozen in the nebula. A small unlock settles in. Pulsations can imprint spacing into the circumstellar medium. Each cycle can add a thin layer. Many layers can later appear as nested arcs. The arcs are not separate events. They are a quiet record of repeated breathing. The next visual anchor appears to keep rhythm while staying secondary. Farther out, a faint pair of concentric edges becomes visible. The outer edge is dimmer. The inner edge is sharper. Between them, the glow is smoother. This is a layering of density from different cycles. The edges drift outward together. Their spacing slowly increases as the flow expands. The analogy remains unique and calm. It is like a slow tide lifting seaweed from rocks. Each high tide leaves a strand higher than before. Each low tide pulls back, but not completely. Over many tides, a line of stranded seaweed climbs the shore. The shore is the escape boundary. The seaweed line is the layered wind. The scale shift widens gently again. The lifted layer may rise a small fraction of the star's radius each cycle. Over many cycles, it can reach distances comparable to a planetary system. Over longer time, it becomes part of a nebula shell. The motion begins as a small lift. It ends as a large geometry. A limit of observation arrives and stays precise. Pulsations are inferred from brightness and spectral changes, yet brightness can also vary due to surface patterns. Spectral lines can shift due to wind acceleration. Multiple processes overlap. This is a limit of attribution. It is also a limit of spatial resolution. The surface cannot be resolved in detail for most supergiants. The inferred radius change is model-dependent. The exact amplitude of pulsation is uncertain. Even with that uncertainty, the role of periodic lifting remains plausible. It is supported by the way layered shells appear in some winds. A small payoff follows from the limitation. The key is not an exact period. The key is that any repeating lift can lower the cost of escape. It turns a steady push into a more effective one. Light can take advantage of the raised gas. Shocks can form where lifted layers meet older outflow. The wind becomes both rhythmic and structured. The scene returns to the detached luminous skin. Its rim drifts outward a little more. Its bumps stretch into short arcs. The arcs are brighter at their crests. Behind them, the glow fades into haze. The star below remains a steady source. The breathing motion continues without urgency. The scale shift widens one last time. A 1-year rhythm can write a pattern that remains visible for 10,000 years. The pattern survives because expansion preserves spacing in a stretched form. The ending transition stays gentle. The next step moves from lifted gas to the making of solid grains in cooler layers. It follows how dust can form more easily in the wake of pulsations. It keeps the wind calm and the edges soft. A massive wind can look smooth from far away, yet its outer boundary is often drawn by dust that drifts and survives. Dust strengthens mass loss by letting light push on solids and then tugging gas along. In that region, light behaves as the steady stream that becomes easier to couple when grains appear. The scene begins in the cooler outflow where the glow is muted. A broad, faint envelope surrounds the star. Its edge shows a soft gradient. Within that gradient, thin, darker lanes cross like gentle shadows. The first unlock arrives early. Dust is not only a passenger, dust becomes a lever that transfers radiation pressure into stronger flow. The first concept stays calm. Grain drift is the relative motion of dust through gas. Grain drift is dust moving slightly faster than surrounding gas. It resembles dry leaves sliding ahead of still air in a corridor. It also resembles fine ash drifting ahead of a slow smoke plume. It matters because drift creates drag. Drag pulls gas outward. The wind gains momentum beyond what gas alone would receive. The unique visual anchor settles and remains central. A narrow dust front forms like a soft-edged wall. It is darker on the inside. It is brighter on the outside where light scatters. The wall is not straight. It bows outward like a slow wave. Along its crest, brightness is higher, because the line of sight passes through more grains. Behind the crest, a faint shadowed trough stretches outward. The wall drifts away as a coherent feature. It is a moving boundary where dust density rises. A small payoff answers a quiet question. Why does the wind often thicken once dust forms? The answer is that grains feel radiation pressure efficiently. They absorb and scatter light. They accelerate. Collisions and electric interactions share that push with gas. The gas does not need to absorb the light directly. The grains act as intermediaries. Once enough grains exist, the outflow becomes easier to drive. The second concept arrives without crowding. Sublimation erases grains when conditions are too hot. Sublimation is a solid turning back into gas when heated. It resembles frost vanishing from a window as warmth returns. It also resembles snow thinning under a rising sun. It matters because it defines where dust can survive. That survival boundary shapes where the dusty wind begins. The physical detail stays concrete. The dust front has a sharper inner edge. Outside it, the haze is thicker but smoother. This indicates a transition. Inside the edge, grains are scarce. Outside grains persist and multiply. Small clumps sit on the edge like soft beads. Each bead is a denser pocket where grains form more readily. The main number arrives and stays rounded. A typical grain is about 1/1,000,000th of a meter across. That is like a speck far smaller than a grain of sand. The number anchors the scale shift. Something so tiny can still influence a shell that spans an orbit. Many grains together can dim and reshape a large region. The next visual anchor appears to keep rhythm while staying secondary. A faint arc brightens where the dust front intersects a denser lane. The arc is thin, it is brighter at its rim. Behind it, the glow fades into a soft cone. This is scattering geometry. Rims appear where the path through dust is longest. Cones appear where light is redirected. A small payoff follows at once. A ring can form from a shell without any rigid boundary. It is the line of sight that selects the rim. Dust makes the rim visible because dust scatters and absorbs. The shell can be diffuse in mass. It can still look sharp in light. The analogy remains unique and calm. It is like flour in a sunbeam over a dark table. The flour is almost weightless, yet the beam reveals it as bright threads and sheets. A slight puff makes a front. The front moves as a soft wall. The beam pushes the flour outward in a gentle drift. The flour then drags the air with it. Dust plays the flour. Light plays the sunbeam. Gas plays the unseen air. The scale shift widens gently again. A grain forms and grows over hours in a cooling parcel. Over years it rides outward and meets older shells. Over thousands of years its collective effect becomes part of a nebula's silhouette. The same grain also changes chemistry. Elements lock into solids. That affects cooling and line emission. It affects how later shocks brighten the region. A limit of observation arrives and stays precise. Grain properties are hard to determine from light alone. Color depends on composition size and temperature. The same reddening can come from many mixtures. Scattering can mimic density changes. This is a limit of degeneracy in interpretation. It is also a limit of spatial resolution. Dust fronts can appear thicker than they are. Models assume size distributions and compositions. Those assumptions change inferred mass loss rates. A small payoff follows from that limitation. Even if details vary, the direction of the effect remains. When dust survives, radiation pressure can couple more strongly to the outflow. That coupling tends to increase acceleration. It tends to amplify structure at the dust boundary. The wind therefore gains a second phase. A hot inner flow becomes a cooler dusty flow. The boundary between them becomes a sculpting surface. The scene returns to the narrow dust wall. It continues drifting outward. Its crest broadens. Its beads stretch into short filaments. The shadowed trough behind it deepens slightly as more grains pile up. The physical detail remains gentle. The edge is soft. The contrast is low, yet the geometry is clear. A moving wall, a brighter rim, a trailing shadow. The scale shift widens one last time. A millionth of a meter grain can help move gas across distances larger than a star system. Over long time, that motion sets where later shells collide. It sets where nebular arcs appear. It sets where brightness concentrates. The ending transition stays soft. The next step moves from dusty coupling to the shaping forces that break symmetry. It follows how rotation and latitude can thicken winds into belts and lobes. It keeps the motion calm and the edges slow. A wind can be driven by a light and dust, yet its final shape depends on how the star's surface is tilted by rotation. Rotation thickens the outflow in some directions and thins it in others, shaping belts and lobes before any final collapse. At this distance, the circumstellar haze is not a uniform sphere. It shows a bright waste and dimmer caps. The waste is a broad band of higher density. The caps are more transparent. A small unlock arrives early. The same wind physics can produce different nebula shapes when effective gravity changes with latitude. The first concept stays calm. Effective gravity is the inward pull after outward forces are considered. Effective gravity is gravity reduced by rotation and radiation effects. It resembles a bowl that becomes shallower when slowly spun. It also resembles water that climbs the sides of a turning cup. It matters because where the bowl is shallow, gas escapes more easily. Rotation changes the bowl differently at different latitudes. The unique visual anchor settles and remains central. A pale hourglass of gas surrounds the star. The waste is a dense, dusty belt. It is darker in the middle and brighter at its rim. The two lobes above and below are fainter. Their edges are soft. The hourglass does not flicker. It drifts outward like a slow breath frozen in shape. Along the waist, a sharp brightness gradient marks a real density jump. The belt casts a gentle shadow into the lobes. A small payoff answers a quiet question. Why does an hourglass appear without an explosion? The answer is that outflow can prefer an equatorial belt. Rotation reduces effective gravity most strongly near the equator. Gas lifted there needs less extra push to leave. Dust can also form more easily in denser equatorial lanes. Radiation pressure on grains then reinforces the belt. The belt thickens. The polar regions remain thinner. A second concept joins without crowding. Centrifugal support is outward tendency from rotation. Centrifugal support is the reduction of inward pull due to spinning. It resembles flour pressed outward in a slowly rotating jar. It also resembles a skirt of mist that flares wider when spun. It matters because it changes the starting density profile. Denser base feeds a stronger wind, a weaker base feeds a gentler wind. The main number arrives and stays rounded. A supergiant can spin once in about 100 days. That is like a slow metronome compared to the star's constant light. The number frames a scale shift. The surface completes a turn over months. The belt it helps create can persist for thousands of years. A pattern made by rotation outlives the rotation that formed it. The next visual anchor appears to keep rhythm while staying secondary. A thin ring forms at the waist's outer edge. The ring is brighter along two arcs. The arcs lie opposite each other. They indicate uneven density within the belt. As the ring expands, it becomes a faint loop around the hourglass. A small payoff resolves another question. Why do some nebulae show rings around an hourglass? The answer is that a dense belt can shed shells. When the wind speed changes, a shock forms within the belt. Compression produces a thin rim. Projection emphasizes that rim as a ring. The ring does not require a separate event. It is a natural byproduct of layered outflow in a preferred plane. The physical detail stays concrete. The belt shows a darker core and brighter edges. That indicates optical depth differences. The brighter edge is where the line of sight crosses more dust. The darker core is where dust blocks forward scattering. Above the belt, faint streaks angle outward. The streaks indicate flow lines into the lobes. They curve gently. Curvature shows the flow is guided by density gradients rather than straight radial motion. The analogy remains unique and calm. It is like syrup poured onto a gently spinning plate. The syrup spreads into a thicker ring near the rim. The center remains thinner. As more syrup arrives, the ring grows outward as a coherent band. Rotation does not create the syrup, it shapes where it accumulates. The scale shift widens gently again. A density enhancement at the base spans a fraction of the star's radius. Farther out, the same enhancement becomes a belt wider than a planetary orbit. Over longer time, the belt defines the nebula's silhouette. The silhouette becomes what is seen first. The small base difference becomes the large outer geometry. A limit of observation arrives and stays precise. Rotation rate is hard to measure directly in a distant star. Spectral lines broaden for many reasons. Turbulence and pulsation can mimic rotation. Wind outflow can also broaden lines. This is a limit of disentangling contributions. Is also a limit of viewing angle. A fast spin seen pole-on can appear slow. A slow spin seen edge-on can appear faster. Models must assume inclination. Those assumptions change inferred centrifugal support. This limits certainty about how strongly rotation shapes a given nebula. A small payoff follows from that limitation. Even without exact spin rates, asymmetric density patterns imply preferred directions. Rotation is one robust way to create such preference. It naturally produces an equatorial enhancement. That enhancement then interacts with radiation and dust. The combined effect can carve lobes and belts. The hourglass shape, therefore, does not require rare conditions. It can emerge from common physics in extreme stars. The scene returns to the hourglass. Its waist remains the brightest feature. Its lobes drift outward and thin. The waist's ring expands and softens. The shadow into the lobes grows wider. The overall structure remains calm. It is a quiet sculpture made by steady flow. The scale shift widens one last time. A 100-day rhythm can guide a structure that remains for 10,000 years. Time stretches the imprint into a nebula. Space stretches it into a silhouette. The ending transition stays gentle. The next step moves from rotation-shaped winds to the guiding effect of magnetic fields. It follows how charged gas can be channeled into arcs and streamers. It keeps the motion slow and the geometry soft. A supergiant wind is mostly ionized gas, and ionized gas can quietly follow invisible curves. Magnetic fields can guide the flow into arcs and streamers before it relaxes into broader expansion. In that region, light behaves as a steady background, while charged particles respond to field geometry. The scene begins close to the star where the halo is brightest. Within that halo, thin luminous threads appear. They curve and reconnect. Some threads form loops that fade at their tops. Others open outward as long streamers. The first unlock arrives early. A magnetic field does not need to dominate the wind to shape its texture. It only needs to organize where the gas begins to flow. The first concept stays calm. Plasma is gas with free charges that respond to fields. Plasma is gas where electrons and ions move separately. It resembles fine dust that aligns in a gentle breeze. It also resembles mist that is guided by subtle channels. It matters because charged gas can be directed. The second concept arrives without crowding. A magnetic field is a region that exerts forces on moving charges. A magnetic field is an invisible structure that guides charged motion. It resembles grooves in a softly molded surface. It also resembles rails that do not touch yet still steer. It matters because those grooves can channel outflow. The unique visual anchor settles and remains central. A crown of faint loops sits above the limb. Each loop is a thin arc of light. The arcs are brighter at their bases. Their tops are dimmer and more diffuse. The loop set looks like a delicate wreath. The wreath slowly rises and stretches. Some loops open into long streamers. The streamers become pale ribbons that curve away from the star. Along each streamer, a narrow, bright spine marks higher density. On either side, a soft gradient fades into the halo. A small payoff answers a quiet question. Why do some winds show ordered arcs in a sea of turbulence? The answer is that magnetic tension can smooth motion along certain directions. Gas moves more easily along a field line than across it. If the base of the wind is threaded by fields, the earliest outflow can be guided. Clumps can be shepherded into lanes. Lanes can merge into a larger streamer. The wind stays free on large scales. It gains order on small scales. The main number arrives and stays rounded. A loop can extend about the width of the sun above the surface. That is like a bridge spanning a whole planetary sky. The number frames the scale shift. The loop forms and evolves over hours or days. The streamer it feeds can drift outward for thousands of years. A small structure near the limb becomes a long filament far away. The next visual anchor appears to keep rhythm while staying secondary. Where a streamer meets the broader wind, a faint kink appears. The kink is a bend where the lane widens. It marks a transition from guided to freer flow. Beyond the kink, the streamer frays into many thinner threads. The fraying is gentle. It is not a violent break. It is the field's influence fading with distance. A small payoff follows at once. The field shapes the launch, not the whole journey. As density drops, the gas becomes less able to hold a coherent channel. The field lines can also open and stretch. The outflow becomes more radial. The streamer's spine remains as a memory of early guidance. The physical detail stays concrete. The loop bases are anchored in brighter patches on the surface. Those patches are slightly darker in the middle. They resemble small foot points where density is higher. From each foot point, a thin, bright strand rises. The strand curves and meets another foot point. At the apex, the strand dims. This is where density and emission drop. Some strands show a faint double edge. That indicates a hollow or layered structure. The analogy remains unique and calm. It is like silk threads draped over a shallow frame. The frame is invisible in the dark. The silk catches faint light and reveals the shape. Where the silk is taut, it forms smooth arcs. Where it loosens, it frays into fine hairs. The wind is the silk, the field is the frame, light reveals the weave. The scale shift widens again. A foot-point region may be smaller than a planetary orbit. A streamer made from many such regions can span distances larger than that orbit. Over longer time, multiple streamers can become the filaments seen in nebulae. The filaments can outline cavities. They can trace the boundaries of older shells. They can also guide where dust collects later. A limit of observation arrives and stays precise. Magnetic fields in distant stars are hard to map. Polarization signals can be weak. Spectral signatures can be blended by wind motion. Turbulence can mimic magnetic broadening. This is a limit of direct measurement. It is also a limit of interpretation. A curved filament might trace a field line. It might also trace a shear layer. The same geometry can arise from different causes. Models use simplified fields and assume symmetries. Real fields can be patchy and time variable. This limits certainty about exact field shapes. A small payoff follows from the limitation. Even if details are uncertain, fields provide a natural organizing influence for plasma. Any non-zero field can align motion locally. That alignment can seed long-lived anisotropies. Those anisotropies then interact with shocks, dust, and rotation. The wind becomes a layered sculpture made from many gentle influences. The scene returns to the wreath of loops. Some loops fade as others brighten. The overall crown remains. The streamers extend outward and slowly straighten. Their bright spines soften into diffuse lanes. The halo becomes smoother with distance. The scale shift widens one last time. A loop that lasts days can leave a filament that persists for 10,000 years. A subtle guiding force near the surface can become a visible strand in a nebula. The ending transition stays gentle. The next step moves from steady guidance to rare, stronger episodes of mass loss. It follows how some supergiants shed brief shells that race outward. It keeps the tone calm and the shapes clear. A supergiant can lose mass quietly for ages, yet it sometimes sheds a thicker layer in a brief phase. Episodic outbursts create dense shells that later shape the surrounding nebula like a slow-moving boundary. At this distance, the circumstellar space shows a new sharp edge. A bright arc appears beyond the older haze. The arc is thin. Behind it, the glow is dimmer and smoother. The first unlock arrives early. A short burst can dominate the visible structure even if it is rare. The wind before and after can be gentler. The shell from the burst becomes the main sculptor. The first concept stays calm. An outburst is a temporary increase in mass loss and wind density. An outburst is a short interval of stronger ejection from outer layers. It resembles a heavy snowfall after a long light flurry. It also resembles a sudden thick fog rolling into a valley. It matters because a dense shell becomes a barrier. Later winds collide with it and brighten its edge. The unique visual anchor settles and remains central. A nearly spherical curtain expands outward. Its rim is bright and narrow. The rim is brighter along one side where the line of sight skims the shell. Inside the curtain, a faint cavity looks darker. Outside, the older wind forms a diffuse background. The shell shows a fine scalloped texture. Small knots sit along the rim like soft beads. Each knot is a denser patch carried along. A small payoff answers a quiet question. Why does a single edge look sharper than everything else? The answer is compression and contrast. A dense shell has a steep density gradient. Light emission and scattering rise sharply at that gradient. The rest of the wind is spread out. It does not concentrate brightness into a line. The shell therefore becomes the dominant feature. The second concept arrives without crowding. A swept-up shell forms when faster flow catches slower material. A swept-up shell is a compressed layer created by collision of flows. It resembles a snowplow pushing a narrow ridge of snow. It also resembles a wavefront gathering floating pollen into a line. It matters because even a mild speed increase can create a strong rim if density is high. A burst provides that density. The main number arrives and stays rounded. An outburst can last about a decade. That is like a brief chapter compared to a long book. The number frames the scale shift. The burst changes the wind for only years. The shell it creates can remain visible for 10,000 years. Time stretches its imprint across the surrounding space. A small unlock settles in. A decade of stronger loss can write a ring that outlives many quieter centuries. The next visual anchor appears to keep rhythm while staying secondary. Along the expanding curtain, a faint double edge becomes visible. The inner edge is sharper. The outer edge is softer. Between them, brightness is slightly lower. This indicates a shell with thickness. The inner boundary is where later wind presses from behind. The outer boundary is where the shell plows into older material. The two edges drift apart slowly as the shell expands. A small payoff follows at once. Two edges can reveal the shell's history. The inner edge traces recent pressure from the inside. The outer edge traces resistance from the outside. If the outer edge brightens, the shell is sweeping more material. If the inner edge brightens, the inside wind is pushing harder. The physical detail stays concrete. The rim is narrow and bright. Immediately behind it lies a darker lane. The lane is a shadowed region where dust blocks forward scattering. Ahead of the rim, the glow is faint and diffuse. This indicates a steep gradient at the rim and lower density outside. Small radial streaks extend inward from the rim. These are fingers of material that have been stretched by the instabilities. They remain thin. They do not form a chaotic spray. The analogy remains unique and calm. It is like a thin layer of varnish poured onto water. The varnish spreads into a smooth film. A gentle current gathers it into a ring. The ring becomes thick at its edge. The interior stays clear. Later ripples push the ring and wrinkle it. The film is the dense shell. The ripples are later winds. The wrinkles are instabilities at the boundary. The scale shift widens gently again. The shell thickness can be smaller than an orbit near the star. Farther out, the same shell can span a region larger than a star system. Expansion keeps the layer thin in relative terms while it grows in absolute size. The shell becomes a moving map of where mass has piled up. A limit of observation arrives and stays precise. The cause of an outburst is hard to reconstruct from the shell alone. Surface pulsations, convection and opacity changes can all increase mass loss. A shell records the result, not the trigger. It is also difficult to measure the shell mass directly. Brightness depends on temperature and dust content. Density can be clumped. Projection mixes near and far sides. This is a limit of inferring mass from light and geometry. Models must assume filling factors and compositions. Those assumptions change the estimated burst strength. A small payoff follows from the limitation. Even without exact mass shell sharpness indicates a brief formation. A long steady wind tends to smear features. A brief enhancement tends to concentrate them. The shell therefore signals episodic behavior. It also explains later structure. When a later wind runs into the shell, a new shock forms. That shock can brighten knots. It can carve arcs. It can create a second ring. The shell becomes the stage for later shaping. The scene returns to the spherical curtain. Its scallops drift outward. The knots on the rim spread slightly. The double edge becomes clearer as the shell expands and cools. The cavity inside grows darker as density drops. The background wind remains as a soft haze. The scale shift widens one last time. Decade of change near the surface becomes a boundary that lasts across 10,000 years. A brief phase becomes a long geometry. The ending transition stays gentle. The next step moves from burst shells to what happens when different winds meet. It follows how a faster, hotter wind can catch a slower, denser one. It keeps the collisions quiet and the shapes clear. A later wind can be faster and thinner, and it can quietly catch the earlier, denser flow. Wind interaction carves cavities and lights up rims when one flow overtakes another. In that region, light behaves as a tracer of pressure and density rather than a simple glow. The scene begins inside the older shell where the space looks darker. A faint inner bubble appears. Its boundary is a smooth arc. Along that arc, brightness rises into a narrow rim. Just beyond the rim, a dim lane suggests a contact region. The first unlock arrives early. A nebula can be shaped from the inside out when a newer wind inflates a hot bubble. The outer shell becomes a wall. The inner bubble becomes the sculptor. The first concept stays calm. Wind interaction is the meeting of two outflows with different speeds and densities. Wind interaction is collision between a later wind and older material. It resembles a smaller wave overtaking a larger, slower swell. It also resembles a brisk current catching a drifting raft of leaves. It matters because the collision makes a layered structure. One layer is shocked inner wind. One layer is shocked older gas. Between them sits a boundary. The unique visual anchor settles and remains central. A glowing inner crescent presses against the inside of an older spherical shell. The crescent is brightest at its edge. The edge is thin and clean. Behind it, the interior looks smoother and fainter. Along the crescent, small scallops form like shallow ripples. Each scallop is a place where the boundary is unstable. The scallops are evenly spaced. They stretch sideways as the bubble expands. A small payoff answers a quiet question. Why does the brightest line often lie inside the old shell? The answer is that the inner shock heats and compresses material at the contact region. Emission rises where density and temperature align. The old shell can remain cooler and dustier. It can be darker in some bands. The inner rim therefore becomes the visible tracer of interaction. The Sund concept arrives without crowding. A contact discontinuity is a boundary between two fluids that do not mix quickly. A contact discontinuity is a surface separating shocked wind and shocked older gas. It resembles oil resting against water with a clear dividing line. It also resembles a glass pane separating warm air and cool air. It matters because pressure can be similar across it while density differs. This creates a sharp edge. It also allows instabilities to grow along the surface. The physical detail stays concrete. The bright rim has a steep gradient. Brightness drops quickly on both sides. The rim also shows a slight double layer. One line is sharper, the other is softer. This hints at two nearby fronts. One front is the inner shock. One front is the compressed older gas. Between them, a thin region holds mixed temperature and density. The main number arrives and stays rounded. The hot inner bubble can reach about 1,000,000 degrees. That is like a furnace compared to the cooler surrounding gas. The number frames the scale shift. The hot bubble is created by gas heated in a thin shock. That shock thickness can be tiny compared to the bubble radius. Yet the hot bubble spans distances larger than a star system. A small unlock settles in. The hottest gas can be the hardest to see. It is too thin to radiate strongly invisible light. The visible rim is often cooler and denser. It forms where the hot bubble presses on the shell. The bubble does the work. The rim shows the work. The next visual anchor appears to keep rhythm while staying secondary. Inside the bubble, faint wisps drift like pale smoke. The wisps curve toward the rim. They appear brighter where they overlap. They fade where the line of sight is shorter. The wisps are not random. They trace flow lines within the cavity. They show that the interior is not still. A small payoff follows at once. The cavity is inflated by pressure, not by a rigid push. Pressure spreads in all directions. It finds weak spots. Where the old shell is thinner, the bubble expands more. Where the shell is denser, expansion slows. This naturally creates a symmetry. A slight density difference can become a visible lobe over time. The analogy remains unique and calm. It is like warm air inside a thin balloon pressing on a patchy rubber skin. Where the rubber is thinner, the balloon bulges. Where the rubber is thicker, it resists. The bulges become lobes. The rubber is the older shell. The warm air is the hot bubble. The pressure is the quiet sculptor. The scale shift widens gently again. A tiny contrast in shell thickness near the star becomes a large cavity far away. Over hundreds of years the cavity grows. Over thousands of years it becomes a dominant shape. The inner bubble also changes the shell's chemistry. It can ionize gas. It can destroy some dust. It can create new emission lines. The visible nebula shifts from dust-dominated to gas-dominated regions. A limit of observation arrives and stays precise. The hot bubble temperature is often inferred indirectly. The interior can be too faint in many bands. Brightness concentrates at rims. Projection mixes the near and far sides of the cavity. This is a limit of line-of-sight confusion. It is also a limit of separating shocks. Two nearby fronts can blur together. Models assume smooth shells. Real shells are clumpy. Clumps can punch through and seed fingers. This changes the inferred pressure balance. It changes the estimated bubble energy. A small payoff follows from the limitation. Even without perfect measurements, rim morphology reveals interaction. Sharp inner rims imply pressure-driven compression. Scalloped edges imply instabilities at a contact surface. Cavities imply a newer wind that is faster or hotter. The nebula therefore becomes a timeline. Older shells provide walls. Newer winds provide inflation. Their meeting draws the arcs that are seen. The scene returns to the glowing inner crescent. Its scallops stretch into longer ripples. The double layer becomes slightly clearer as the bubble expands. The older shell ahead remains a pale wall with knots and shadows. The cavity behind stays smooth and faint. The scale shift widens one last time. A shock front that forms in seconds can define a rim visible for thousands of years. A pressure difference created near the star can carve a cavity larger than an orbit. The ending transition stays gentle. The next step moves from interacting winds to how these structures seed the final nebula before collapse. It follows the slow widening of consequences in the surrounding medium. It keeps the motion calm and the edges soft. A nebula can look like a still portrait, yet it is a moving record of pressure cooling and mixing. Cooling turns compressed gas into thin, bright skins and dark lanes, preserving shapes that would otherwise blur. In that region, light behaves as a thermometer and a shadow maker. The scene begins at the rim where the inner bubble presses on older material. A thin, bright line traces the boundary. Immediately behind it, a softer glow fades inward. Immediately ahead, a darker lane stretches outward along the shell. The first unlock arrives early. Cooling decides which parts of an interaction remain visible. Where cooling is efficient, the rim becomes thin and sharp. Where cooling is slow, the boundary stays broad and faint. The first concept stays calm. Radiative cooling is energy lost as light from hot gas. Radiative cooling is gas shedding heat by emitting photons. It resembles a hot stone dimming after sunset. It also resembles steam fading as it spreads and cools. It matters because cooling increases density at the boundary. Dense gas forms a thin skin that can hold a shape. The unique visual anchor settles and remains central. A layered curtain appears at the interaction front. The outermost layer is a narrow, luminous thread. Just behind it lies a darker band. Behind that band is a faintly glowing sheet that looks thicker and smoother. The thread wavers in small scallops. The scallops are shallow and regularly spaced. Along the scallops, tiny knots brighten and soften. The curtain drifts outward as a coherent boundary. Its layers remain parallel. The physical detail stays concrete. The luminous thread has a sharp edge. The dark band is a shadowed trough with a steep gradient. The faint sheet behind it shows a gentle texture like brushed haze. This layered look indicates a cooling zone. The hot side is smoother. The cooled side is thinner and denser. A small payoff answers a quiet question. Why does a rim often have a bright line plus a dark lane? The answer is that emission and absorption can sit next to each other. The compressed layer emits strongly. Dust or neutral gas nearby can absorb or scatter, producing a lane. Geometry amplifies the contrast. A line of sight can skim the bright skin while crossing the darker band. The pair becomes a clear marker of where energy is being lost. The second concept arrives without crowding. A cooling length is the distance gas travels while cooling significantly. A cooling length is how far shocked gas moves before losing heat. It resembles a road where fog thins after a set distance. It also resembles a river reach where warm water becomes cool again. It matters because it sets rim thickness. Short cooling length makes a narrow skin. Long cooling length makes a broad zone. The main number arrives and stays rounded. A bright cooling skin can be about 1% as thick as its radius. That is like a thin peel on a large fruit. The number frames the scale shift. The peel is thin locally. The fruit is enormous in absolute size. A small local thickness can still define the whole silhouette. The next visual anchor appears to keep rhythm while staying secondary. Farther along the shell, faint ripples spread like shallow waves. Each ripple is a slight brightness change. The ripples curve and merge. They are more visible where the shell is denser. Where the shell is thinner, the ripples fade into smoothness. This shows that cooling is not uniform. Density changes cooling efficiency. A small payoff follows at once. Cooling can amplify small density differences. A slightly denser patch cools faster. Faster cooling increases density further. The patch becomes a knot. The knot shadows the region behind it. The shell becomes clumpy without any violent trigger. It is a quiet feedback. The analogy remains unique and calm. It is like glaze on cooling pottery. Where the glaze is a little thicker, it cools and hardens sooner. That early hardening preserves a ridge. Nearby thinner glaze stays soft longer and levels out. The final surface shows sharp ridges next to smooth zones. The rim is the hardened ridge. The diffuse interior is the leveled glaze. The scale shift widens gently again. Cooling acts on particles and atoms at microscopic scales. Their emission lines and collisions decide how quickly heat leaves. Yet the result appears as macroscopic structure. It becomes arcs, filaments and cavities measured in many stellar radii. Over thousands of years, the nebula becomes a museum of cooling outcomes. Shapes that cool into thin skin survive. Shapes that do not cool become diffuse and forgettable. A limit of observation arrives and stays precise. Cooling rates depend on composition and ionization. Those are hard to measure precisely across a complex nebula. Line emission can be blended along the line of sight. Dust absorption can mimic low temperature by dimming light. This is a limit of disentangling temperature and extinction. It is also a limit of spatial resolution. Thin skins can be narrower than the available resolution. They can appear thicker than they are. Models must assume filling factors and clump sizes. Those assumptions change inferred cooling length and density. A small payoff follows from the limitation. Even with uncertainty, relative contrast still teach structure. A sharp rim indicates short cooling length compared to radius. A broad glow indicates longer cooling length. A dark lane indicates dust or neutral layers adjacent to emission. Together, these features map where energy is being lost and where matter is piling up. The scene returns to the layered curtain. The luminous thread remains narrow. The dark band remains steady. The faint sheet behind it expands and smooths. The scallops stretch into longer arcs as the shell grows. The knots separate slightly as expansion increases spacing. The scale shift widens one last time. A thin, cooling skin can form quickly in a shock. That skin can remain visible for thousands of years as it expands. A microscopic emission process becomes a cosmic outline. The ending transition stays gentle. The next step moves from cooling-shaped boundaries to the broader consequences for surrounding space. It follows how these winds enrich and precondition the medium before the final end. It keeps the tone calm and the geometry soft. The space around a supergiant becomes quieter as distance grows, yet it also becomes more consequential. The wind deposits material and structure into the surrounding medium, preconditioning what happens when the star finally ends. In that region, light behaves as a soft veil over a much larger reservoir of matter. The scene begins far from the bright inner rims. The nebula fades into a wide, faint glow. The glow is not uniform. It shows gentle mottling. It shows broad arcs that are almost invisible. Along one side, a long, faint ridge curves outward. Along the other, a subtle hollow looks slightly darker. The first unlock arrives early. The most important shaping can happen after the brightest phase when the wind's products drift into wider space. The nebula is not only a picture, it is a prepared environment. It becomes a buffer. It becomes a map of where material accumulates. The first concept stays calm. Enrichment is adding heavy elements and dust to surrounding gas. Enrichment is the spread of newly made atoms into space. It resembles spice diffusing into a large pot of soup. It also resembles fine pigment mixing into wet paper. It matters because composition changes cooling and dust formation later. It also changes how future shocks brighten. The unique visual anchor settles and remains central. A distant bow-shaped ridge arcs through the faint outskirts. The ridge is broad and dim. Its leading edge is slightly brighter than its trailing side. The ridge has a smooth curvature. Along its crest, small lumps create a wavy outline. Behind the crest, a gentle gradient fades inward. Ahead of it, the background looks smoother. The physical detail stays concrete. The ridge shows a compressed front with a brighter outer lip. Just behind that lip lies a thin, darker lane. The darker lane indicates lower emission or more absorption. The crest also shows faint striations that run along the arc. These striations are parallel lines of slightly different brightness. They hint at layered deposition from earlier wind phases. A small payoff answers a quiet question. Why does a distant ridge appear even when the inner nebula is faint? The answer is that the wind meets external resistance. Where ambient density is higher, material piles up. A ridge forms as a slow compression. It is not a violent shock in appearance. It is a broad gathering. The ridge is a place where the wind's momentum finally distributes into the surroundings. The second concept arrives without crowding. A circumstellar medium is the gas and dust surrounding a star from its own loss. A circumstellar medium is the envelope built by winds over long time. It resembles a layered shoreline built by repeated gentle tides. It also resembles rings of sediment laid down in a shallow basin. It matters because it sets the stage for the final explosion or collapse. It determines where energy will go. It determines what shapes will be illuminated later. The main number arrives and stays rounded. The outer envelope can extend for about 10,000 years of expansion. That is like an old grove growing from a single season of seeds. The number frames the scale shift. The star changes from month to month at its surface. The envelope records changes across millennia. Each outburst and lull becomes a layer that travels outward. The layers become faint arcs far away. A small unlock settles in. Time itself becomes a sculpting tool. The wind does not need to be strong to matter at large scales. It only needs persistence. A long, gentle loss can build a large reservoir. A brief burst can add a sharp layer inside it. Together they make a stratified environment. The next visual anchor appears to keep rhythm while staying secondary. In the faint outskirts, a wide shell shows a subtle double boundary. The inner boundary is slightly brighter. The outer boundary is smoother. Between them is a broad region of weak emission. The broadness suggests slow compression rather than a narrow shock. The double boundary suggests 2 episodes of pressure. A small payoff follows at once. Even in the outskirts, layered history remains readable. A second boundary can mark an older shell overtaken by a later one. It can also mark a region where cooling changes the brightness. It shows that mass loss is not a single event. It is a sequence that keeps spacing as it expands. The analogy remains unique and calm. It is like a stack of thin sheets drifting across a still pond. Each sheet is almost transparent. Where 2 sheets overlap, a slightly darker band appears. Where a sheet meets a gentle current, its edge gathers into a soft ridge. The pond is the surrounding medium. The sheets are successive wind layers. Overlap reveals layering without sharp motion. The scale shift widens gently again. At microscopic scales, a dust grain forms when atoms stick on a surface. At large scales, countless grains create broad lanes of absorption. Tiny differences in composition change how the gas cools. Those differences decide whether a distant ridge glows or stays dim. Over millennia, small chemistry becomes large structure. The envelope becomes a patchwork that varies in cooling and opacity. A limit of observation arrives and stays precise. The faint outskirts are difficult to measure. Surface brightness drops below many detection limits. Background emission can confuse the boundary. Dust can hide gas, and gas emission can hide dust. This is a limit of sensitivity. It is also a limit of separating circumstellar material from the interstellar background. A ridge might belong partly to the wind and partly to the ambient medium. Projection can place unrelated filaments on top of each other. Models must assume a 3-dimensional shape from a 2-dimensional image. Those assumptions change inferred mass distribution. A small payoff follows from the limitation. Even with uncertainty, the existence of faint outer arcs implies long-lived mass loss. A broad bow-shaped ridge implies interaction with surrounding density. A double boundary implies episodic layers. These clues show how the wind preconditions space. The environment becomes denser in some directions. It becomes more open in others. When the final event arrives, its energy meets this prepared landscape. It will brighten ridges. It will carve cavities. It will follow paths of least resistance. The scene returns to the distant bow-shaped ridge. Its crest remains steady and smooth. The wavy lumps along it drift outward very slowly. The inner nebula is now only a dim glow behind it. The outer background becomes a quiet field of mottled light. The scale shift widens one last time. A grain-sized signaled process leaves a lane that spans many stellar radii. A millennium of wind leaves an arc that can steer a sudden final blast. The ending transition stays gentle. The next step moves toward the final quiet resolution of the arc. It follows how the accumulated structure sets a soft frame for the end. It keeps the focus on shape and consequence without suspense. The last quiet understanding is that a supergiant wind is not only loss, it is a way the star writes its boundary into space before anything final occurs. The wind shapes nebulae by layering compressing and cooling matter over long time. At this distance, light behaves as a gentle tracer of edges and gradients. The scene begins with the full structure held at once. A faint outer arc curves like a wide halo. Inside it, a softer shell glows unevenly. Deeper still, thin rims and filaments outline older pushes and pauses. Between bright features, shadowed lanes drift like slow rivers of darkness. The first unlock arrives early. The nebula is a memory of changing winds. It is also a set of conditions that guides what comes later. The arc is not a decoration. It is a physical arrangement of density and composition. The first concept stays calm. Momentum is motion carried by moving mass. Momentum is how a flow keeps pushing even as it spreads. It resembles a slow rolling wave that continues after the wind stops. It also resembles a heavy curtain that keeps sliding after being tugged. It matters because momentum sets where matter piles up. It decides where ridges form. It decides where cavities remain open. The unique visual anchor settles and remains central. A broad nested set of arcs appears like contour lines on a quiet map. The outermost arc is faint and smooth. The next arc inward is brighter and more mottled. A third arc is thinner and sharper. Along that third arc, small scallops repeat gently. Between arcs, the glow changes gradually. The gradient is steady rather than abrupt. The physical detail stays concrete. Each arc shows a brighter leading edge and a softer trailing side. The crest has a subtle ridge. The ridge casts a faint shadow lane just behind it. The shadow lane is not a hard cut. It is a smooth dimming that follows the curvature. This geometry is a signature of layered compression and cooling. A small payoff answers a quiet question. How can a wind make both smooth arcs and clumpy knots? The answer is that the wind sets a large-scale push. Cooling and density differences refine the details. The broad arcs come from long-term momentum and expansion. The knots come from local cooling and instabilities in compressed skins. Both exist because the wind is variable. Both persist because expansion carries patterns outward without erasing them quickly. The second concept arrives without crowding. A density gradient is a smooth change in density across space. A density gradient is how material thickens from one region to another. It resembles fog that becomes thicker toward a valley. It also resembles sand that deepens toward the base of a dune. It matters because gradients bend shocks and brighten rims. They also create shadows by changing absorption. They decide which features look sharp and which look soft. The main number arrives and stays rounded. A dense shell can travel outward for about 10,000 years. That is like a long history preserved in a single slow drift. The number frames the scale shift. A change near the star can happen in days. The resulting shell can remain visible over millennia. Small changes accumulate into a layered archive. Each layer moves outward and keeps spacing that can still be read later. A small unlock settles in. The wind does not only remove mass, it transfers pattern. Pattern becomes density contrasts. Density contrasts become light and shadow. The nebula becomes a readable object even without any sharp event. The next visual anchor appears to keep rhythm while staying secondary. Along the inner arcs, a thin filament splits into two strands. The strands run parallel for a long distance. Between them, a narrow dark seam remains. The seam follows every curve. It shows that two layers overlap along the line of sight. It also shows that dust or neutral gas sits between emitting skins. A small payoff follows at once. A split filament suggests layered flow. A single boundary can become two when a later wind overtakes an earlier one. The earlier shell slows as it sweeps ambient gas. The later shell catches up and compresses it again. The overlap creates parallel strands. The dark seam appears where absorption increases or emission drops. The filament becomes a simple marker of sequence. The third concept arrives gently and completes the set. A termination shock is where a wind slows abruptly against surrounding pressure. A termination shock is the boundary where outflow meets resistance and heats. It resembles a moving crowd that slows at a narrow doorway. It also resembles a river that widens and loses speed at a marsh edge. It matters because it sets the inner rim. It creates hot gas that can glow and push. It also sets where cooling skins can form. The scale shift widens one more time. At microscopic scales, atoms collide and emit light. At macroscopic scales, that emission draws the outline of a shock. The outline becomes an arc that spans huge distances. Over millennia, repeated boundaries create nested contours. The nebula becomes a quiet record of energy flow. It shows where the wind spends its momentum. It shows where cooling locks shapes in place. A limit of observation arrives and stays precise. The full three-dimensional structure cannot be seen directly. Projection hides depth and overlaps unrelated layers. Emission lines blend along the line of sight. Dust can dim and redden, making hot gas look faint. This is a limit of disentangling geometry from brightness. It is also a limit of sensitivity in the faint outskirts. Outer arcs can fade into background emission. Models must assume symmetry or clump sizes that cannot be resolved. Those assumptions change inferred masses and energies. A small payoff follows from the limitation. Even without perfect reconstruction, certain cues remain robust. Sharp rims imply short cooling zones and strong compression. Broad glows imply longer cooling and smoother gradients. Split filaments imply layered history and overtaking flows. Outer arcs imply long-lived mass loss and interaction with the surrounding medium. Together, these cues show how massive stars shape nebulae before they die. The scene settles into stillness again. The nested arcs remain like quiet contour lines. The filaments soften as distance grows. The shadow lanes remain as gentle dimmings, not harsh voids. Light fades gradually across the gradient. The final scale shift arrives softly. A single grain can help create a dark seam. 1,000 years can create a shell. 10,000 years can create an outer halo that guides later motion. The wind becomes a slow sculptor. The ending transition remains calm and closed. The arc of wind's shells and cooling now rests as a complete picture. The next silence is simply the nebula drifting outward. It keeps its layered memory while the light slowly thins.